M0n, and the other is AMN, as in Aluffi, Marcoli, Nascimento, explicit formulas for the Grothendieck class. And they are on the archive, as you can tell. If you Google something that reminds you of the title, then you should find them. So M0n bar will denote the modular space of stable n-pointed genus zero curves. Depending on your background, you may be very familiar with this object or not at all familiar. So I will quickly state the result and then make sure that I talk about this object, which is a beautiful object that everybody should know about. So here's the theorem. Varieties have a class in the Grothendieck group or ring of varieties. L is the, I should be able to point, right? This fancy L over here is the class of the affine line, also called the Lefschetz state module. And here's the formula for the class of the stable, the space, or the modular space of stable n-pointed genus zero curve in the Grothendieck ring. So it is a very simple polynomial in L times an expression which may look a little, I don't know, awkward or complicated, but its value, it's completely explicit. So again, it's a series expressed in terms of the powers of the class of the affine line, and these little s and big S are Stirling numbers. There's two kinds of Stirling numbers, first and second kind. And again, if you are combinatorially inclined, you know exactly what the Stirling numbers are. And if you are like me, maybe a little less familiar with these objects, then you benefit from a little reminder, and this will come. Remind you also that M0 n bar is a smooth projective variety of dimension n-3. M03 bar is a point, M04 bar is P1, and there's many more. I will, in 10 minutes, I will tell you about these spaces more in detail. And if you, let's see, maybe I can, there we go. If you use the formula I just put on the board, then this is the list of Grothendieck classes. They're just friendly-looking polynomials. There are things about them that should be immediately visible. For example, they are palindromic, right? The coefficient here is the same as the coefficient there. This is not surprising. This has to do with the fact that indeed M0 n bar is a smooth projective variety. So the individual coefficients are the Betti numbers. So if you are topologically inclined and you work over C, then the coefficients in this big table we had a moment ago are simply Betti numbers of this nice smooth projective variety. And out of the explicit formula I put a couple of slides ago, you can get this explicit expression for the Betti number, the 2/11th Betti number of M0 n bar. If you know M0 n bar, then you know that the odd cohomology is 0, so those are the only pieces of information in the story. So going back to what I showed you, the formula that I had before, I'm tempted to put it again. It's just a combination of Stirling numbers. It looks like this. So it should be obvious that this is palindromic, right? That there's this equality of coefficients, and it's not combinatorially obvious. No, the only reason I know it's palindromic is because I know something about smooth projective varieties. It's also clear from the geometry, just because this is an n-3 dimensional variety, that this is a polynomial of degree n-3. So these numbers should be 0 for L greater than n-3. And again, I don't know, you may be much stronger combinatorially than I, but I cannot see this from the formula. In fact, I asked Don Zaguet, who's probably the cleverest person on the planet, and even he could not see immediately that this is 0 for L greater than n-3. So let me remind you of what all these things mean. I mean, you are certainly familiar with Betti numbers, so that makes sense. You may be familiar with the Grothendieck class. I will say a word about that. You may be familiar with the modular space, but I'll say something about that as well. And even Stirling numbers. These are very basic notions, but they're not really part of my curriculum, so you may also be not too familiar with them. They're very simple numbers. They are the change of basis coefficients if you want to go from the basis of polynomials given by monomials, powers of x, and these gadgets called following factorial for obvious reasons. If you plug x equals a number, you get the first from the top down, the first expression for the factorial. So these are polynomials, and you just read off coefficients in when you go from one basis to the other, and that gives you the Stirling numbers. So for example, take for n equals 3, then the following factorial is just x cubed minus 3x squared plus 2x, and that tells you that the first Stirling number, sorry, the Stirling number of the first kind for 3, 3 is 1, the Stirling number of the first kind for 3, 2 is -3, and so on. I mean, you just read off the coefficients. Now, this should be as famous as binomial coefficients. Binomial coefficients are ways to go from the basis of powers of x to the basis of binomials, not powers of binomials. And this is just a different choice of basis. It looks like my slides are a little, maybe like this would be better. Okay. It's a nice exercise to compute the second kind, so the inverse matrix, and it's a simple formula in terms of factorials. The formula for the first numbers of the first kind, there is a formula, but it's much harder and it's not pleasant to look at it, so I will not show it to you. But no, since these are change of basis for two different bases, you can put them in a matrix and there will be something clear about them. So in matrix form, what I just showed you, these 1, -3, 2 show up over here. There we go. So you can make a matrix of Stirling numbers of the first kind, and you can make a matrix of Stirling number of the second kind. These are really change of base matrices, so they are inverse to one another. So if you want to know the Stirling number of the second kind, one way to do it is to use the easy formula I told you for the first kind and then invert the matrix, and that gives you this beautiful matrix. I need a notation for the next thing I want to tell you. I will call 1 sub q the diagonal, infinite diagonal matrix with increasing powers of q in the entries. And I will call the kth trace the sum of the entries in the kth subdiagonal. So the ordinary trace is the sum of bases of the entries in the usual diagonal. The first trace will be here, the second trace will be here, and so on and so forth. So try to keep that in mind for a second, and then I want to just show a little computation. I advertise that the matrices for Stirling numbers of the first kind and the second kind are inverses to one another, so here's that statement again. You cannot stop me from putting identity matrices, infinite identity matrices in this computation. That doesn't change the result. And with the notation I introduced, the identity is 1 sub 1, so it's powers of 1 along the diagonal. So this is still true. Now what I want to do is change these guys here. Rather than 1, 1, and 1, I'm going to put L inverse, and L. What is L? Take it as a variable, but we know that secretly this is the Grothendieck class of the affine line. If you do this computation, this is what you get. So this is how you can instruct your Maple to do this in 1 second. And I don't know if it is very visible on your screen, but these entries are red, just because I want to highlight at least one of these guys. So this is, using the notation I introduced a moment ago, the first trace of this matrix. The first trace, there we go, of this is the sum of these terms, 1 minus L plus 3L minus 3L squared, so on and so forth. If you do this sum, then you discover this very simple expression. And we teach calculus, so we all know that this is the inverse of a simple polynomial. It's 1 minus L squared. That's the inverse of this our series. So the statement here is that 1 minus L squared times the first trace of this is 1. And 1 happens to be the Grothendieck class of M03 bar because, as I reminded you a moment ago, and as we'll discuss in a moment, this is a point. And I'm writing it in this funny way because this is another statement, another version of the main result. So that formula I put on the first slide with complicated Stirling numbers is actually just this. It's a very simple polynomial, 1 minus L to the n minus 1, times a trace of this big matrix that I've written over here. I find this somehow aesthetically more pleasant than the written out version. But, okay, so that's what we are talking about, this theorem. Any question? If you can, feel free to stop me anytime, of course. No question, so I'll go back to a bit of its history so that all of us are familiar with this space. The definition of and the construction of this space, the space of stable end-pointed genus zero curves, goes back to Knudsen in 1983. And after that work, there were several alternative constructions. I should mention Kapranov, that I don't think I will mention elsewhere in these notes, but the one I want to focus on is Keel's construction, that is about 10 years later. It was part of his PhD thesis. I know because I was in Chicago when he was a graduate student of Fulton, and I remember him talking about this. So this leads to a determination of the cohomology or equivalent information of the Chow ring. A stands for the Chow ring. If you know what that means, you're very good. Otherwise, just take it as an expression of the cohomology. Now, over C, that's exactly right in this case. The Chow ring exists over any field, so it's somewhat a more general object, and whatever I say will apply to that context. But let's stick to Bethe numbers. Those are nice things to think about. So Keel proved this fact that I reminded you a moment ago, that the odd cohomology is 0. He proved that in this case the Chow ring is isomorphic to the cohomology ring, and got a recursion for the rank of H12, for the 12th Bethe number. This is beautiful work. I mean, we are going back 30 years, but it is really spectacularly nice. So with this notation, I'm using Keel's notation in his paper. Then you have this recursion. AK3 is 1 if k equals 0 and 0. Otherwise, this is just saying that M03 bar is a point. So the class of a point is 1 in this ring. And then I have to tell you how to go from 1 to the next, and this is what Sean Keel states and proves. It's a somewhat complicated formula involving the nth level Bethe numbers and even the lower level Bethe numbers combined in this curious fashion. That's how you go from one to the next. So this information is enough to reconstruct this big tree of classes I showed you a moment ago. There were other proofs of this recursion or recurring information. There's a paper, very influential paper by Fulton McPherson on configuration spaces that has material that you can use to prove this. There's a beautiful paper by Getzler, and there's a paper by Manin, and again, I'm highlighting it because I want to focus on it, from 1995. So let me tell you what he did. He puts all the information in a generating function. So this is the Poincare polynomial. It's another version of my Grothendieck class. It's essentially the same information. But if you're topologically inclined, you may be happier to think about the Poincare polynomial. It's just Bethe numbers with powers of a variable. So put those in a generating function. And then the task is to say something about this function M. And he does. In this paper, Generating Functions in Algebraic Geometry and Sums over Threes, he proves that there is a nice differential equation and a functional equation that determines this function. It will come in a moment. Again, this is just to connect the class in the Grothendieck group with the Poincare polynomial. Take the Poincare polynomial, replace t by t squared by L. I told you that the odd cohomology is 0, so the coefficients of the odd powers of t are 0. Replace the even powers of t with powers of this variable L, which we know stands for the Grothendieck class of the affine line. And then this is the version of the generating function I had on the previous slide, and I can state Manin's results in the version that Manin and Marcolli obtained a little later. So the derivative of n with respect to z is this rather simple expression involving the function you are after and the Lefschetz state class. And then there's this other version of the same information. It's a functional equation This is a formal object. You can take it as the exponential of L times logarithm of m. Those things are computable, and then that defines a sensible notion of a power of m. And again, a very simple expression in terms of that information. I'm looking again for my pointer. I hope this is it. There you go. Okay, so this is maybe more pleasant than Keel's version of the recursion, but it is the same information. And Manin obtains it very differently. Keel has an inductive construction, which I remind you of in a moment. Manin does this by a concrete computation of sums over trees, and again, that will make more sense. Sorry, there's a cat coming by, but no, it's not. There you go. Okay, so our contribution is to solve these equations. So, it was a little astonishing that these things had been around for 30 years. 1995 is exactly 30 years ago. And evidently people had not tried seriously or wanted to solve these equations. But these are differential equations. I'm an algebraic geometer. I'm not supposed to be able to solve differential equations, but we tried hard until we did find a solution. So here's the theorem. It's again the same information as in the first slide, but written out as a generating function. It's not so pleasant looking. If you are like me, you cannot possibly absorb this by looking at it on a screen in a room full of people, but the ingredients are not that bad. I mean, it's a power series in here with some factorials and powers of the index, and then some expression that involves all these ingredients. Again, there's a power that looks a little mysterious. Whenever I write something like this, you should think of the exponential of the exponent times the logarithm of this. And if you are, you could go to Maple and ask to work this out. It will produce a beautiful series that corresponds to it. This is one version of the statement. You can massage it into this other version, which I find a little more friendly looking. At least the power is not fancy power, it's just a power of with an integer exponent. And it's good to have both of these. The second form implies the Stirling expression that I put on the slide at the beginning. The first is what you really get if you work out the solution of the equation, and it's independently useful, and it implies the second. So this is how we get it. All right, so I think I'm ready to start the talk. In a sense, this was just an introduction to show what the result is, but to make contact with people who may not have this background as, again, if I talk to a random algebraic geometer, they may or may not know what this space really stands for, and it's a beautiful space, so I want to advertise it. I will say something about Grothendieck classes. I will even sketch a proof of what we do. It's cheating in a sense. You prove something, it takes weeks for you to figure something out, and then after the fact, you realize what you should have done. And if you had done that, then you would have proved your theorem much faster. So I can condense a very quick proof in a couple of slides, and it's the after the fact, the post-mortem kind of consideration. And then I will end with one consequence, which I find charming, and some contextual comments, and also comments on more recent work that happened after we did this. This is something we obtained about a year ago. And since then, people have looked at this from different perspectives. Okay, again, any question? This is a good stopping point. If you're not familiar with M0 and bar, everything I said so far is a little foggy, although I told you the coefficients you care about are just the numbers of this variety, so at least you know what those may mean, but you have to know what the variety is. So let me first tell you something about the modular space of genus 0 and pointed curves without the bar, so without compactifying. And this is a workshop in algebraic geometry, so you're all familiar with the fact that in algebraic geometry, we have this beautiful luxury of defining spaces that parameterize families of interesting spaces. The main example is the projective space. Projective space parameterizes one-dimensional subspaces of a fixed vector space. And it's mild generalization. The Grassmannian does the same, but for k-dimensional subspaces. These are algebraic varieties, and their job is to parameterize other algebraic varieties. In fact, the fanciest, most popular one is maybe MG, the modular space of genus G curves, which parameterizes isomorphism classes of genus G curves. Now, if you know a bit of the story, you know that sometimes you're very lucky, sometimes you're not so lucky. You're very lucky when you're in a situation like this, because then there's a functor you can define, and the variety you mentioned, the projective space of Grassmannian, represents that functor. So it's a very kind of simple situation. You're less lucky in this case because the scheme that you can call MG doesn't quite correspond to the functor. No. If you don't know about this, go and look at the literature. It's a very interesting story. But we are lucky in this case because for M0 that will not be an issue. All these are modular spaces, and to be a modular space is a stronger requirement than just parameterizing objects. I mentioned the word functor. There's a functor that you want to represent, and that's what you're really aiming at. And part of that information is this. For example, for the Grassmannian, there is a universal subbundle of this trivial bundle of the Grassmannian, defined in a very intuitive way. The Grassmannian parameterizes subspaces. Well, give me a point of the Grassmannian. That should be a subspace. And well, make that the fiber of this bundle. So you can create a bundle that has the property that the fibers of this bundle are precisely the spaces corresponding to the points down here. So this is called the universal subbundle. It's doing a universal job, right? Universal in the categorical sense. Now, if you want to, after you define the Grassmannian, if you want to parameterize a family of subspaces of a fixed space, all you need to do is map to the Grassmannian and pull back this bundle. I'm talking about the Grassmannian because maybe the average person is more familiar with Grassmannians, but the same story happens for curves, for the modular space of curves. Oops, there is a universal curve whose job is to represent the curves that a point in the modular space is associated with. So there we go. I will have a diagram in a moment. I wanted the diagram. Where's the diagram? No diagram. Too bad. So the universal curve is called CG, and it does the same as the universal bundle did for Grassmannian. So over a point of the modular space, a point of the modular space is an isomorphism class of a curve. Over the point, put the curve. So the fiber over the point of modular space corresponding to C is the curve C, or rather a curve with that isomorphism class. It turns out that CG can be expressed itself as a modular space. It's parameterizing, and this is very intuitive and of course can be made reverse. It's parameterizing curve C and then a point on the curve. If you want to recreate the curve, that's what you need to do. Once you fix the curve, you have to give me the points of the curve. Well, put them as fibers of a fibration, and that reproduces this universal curve. So you can view it as a modular space that parameterizes curves of a given genus, and then a point on the curve. Let me call this MG1. It's most common denomination. You can do this many times. You can create a modular space MGN, which parameterizes genus G curves, along with a choice of distinct points. And let me point out that these are supposed to be distinct and that they are ordered. Now, you can make different choices and get different spaces, but that's the convention. The universal curve over this is just adding a point. And the map from the universal curve to MGN forgets the last point. This is for all genera, but I only care about genus 0. Now, my title said the stable endpointed curves of genus 0. And then there's not much to parameterize for genus 0 curves. There's exactly one genus 0 smooth projective curve up to isomorphism. It's P1. And I draw it as a sphere because if you are over the complex numbers, P1 is a sphere. So M0n should be that sphere. There's nothing to parameterize there, along with the choice of n distinct points. It's now something you can really, I can picture in my mind easily. I just choose n points, keeping them ordered, and this is important, letting them distinct on a sphere. However, drawing spheres is cumbersome, and after all, this is just a snapshot, a combinatorial snapshot, so you might as well use this. Now, this line over here is supposed to be P1, And you're just telling the reader, look, I'm choosing a bunch of points. They are all distinct, and there's n of them. So that's my caricature for this kind of objects. You want these things up to isomorphism, and as you certainly know, P1 has automorphism, has lots of automorphisms. So in this case, it's up to a Möbius transformation, three-dimensional object. So it's the same as fixing where the first 3 points are. Up to a Möbius transformation, you can take any 3 of these points and make them 0, 1, and infinity. So let's decide that P1, P2, P3 are 0, 1, and infinity, and then the rest is going to be what the space parameterizes. With this in mind, for n less than or equal to 2, then you just ignore this because there's too many automorphisms. You don't want to mess with that at this if you want to stay within this context. The first one that is not drawable is M03. The first 3 points are 0, 1, and infinity, and once you fix those, there's nothing else. So this is why M03 is a point, something that I mentioned several times already. What about M04? Well, you have to fix the first point, the second point, and the third point, and then the fourth point can move more or less freely. The only constraint it has is that it should not be one of the 3 special points. So P4 can be moving freely on a P1, but it has to avoid 3 points. As a result, it just so happens that M04 is this variety. It's P1 minus the points 0, 1, and infinity, and the reason is that P4 is not allowed to be 0, 1, or infinity. Okay, so even with this, you could go, and if you've never seen this before, you can start dreaming up how these spaces are put together. For example, M05, I have to give fixed 3 points and then give 2 points. To give 1 point is M04, to give the other point is another copy of M04, and the only thing you should avoid is that those points should not be the same. So literally M05 is P1 minus 0, 1, infinity, cross P1 minus 0, 1, infinity, minus the diagonal. The dimension is 2, as you should expect. Okay, so you can make a nice inductive construction of this. M06, for the same reason, is product of 3 M04s minus the diagonals, and so on. This already hints like to the fact that there's inductive constructions of these objects. M0n is an n minus 3 dimensional smooth variety, and it's the complement of diagonals in a power of a rather friendly object. This is just P1 minus 0, 1, infinity. However, you always want, if you can, to work with compact objects. Intersection theory, for example, works better on compact varieties than on non-compact varieties. So you look for a compactification of this. Why is this not compact? Because as Pi comes to Pj, they cannot collide. There's no limit as, imagine you have 2 points that are trying to come together and the limit is not in this space. So a natural question is, can you find a good compactification? Good means modular, so it should be something that parameterizes objects, represents a functor. It should be as clever as M0n, but should allow points to collide to some extent. So if you go down the list, M03 bar, you have no choice. The point is already compact and there's no problem there. For M04 bar, M04 is P1 minus 0, 1, infinity. There's only one curve that compactifies that, so there's no other choice. It must be P1. M05 is the first interesting one. How do you compactify M05? And I still have M05 up here. A compactification of this is P1, and compactification of that is P1. Diagonals would be absorbed in the compactification, so you might guess that M05 bar should be P1 cross P1. And this is sad on one hand and very interesting on the other hand. This doesn't work. You cannot view it as a modular space. And if we had more time, it would be nice to go into the reason why that is the case. The point is that you want to parameterize limiting positional points. Well, that will depend on which points you choose to call 0, 1, and infinity if you make this choice. So it's not as good as it should be. This probably was, I'm very old, but not old enough to remember what the situation was before 1983, but in 1983, Knudsen was able to construct a modular compactification of M0n. So each point of M0n corresponds to something. Sorry, each point of M0n bar of the compactification corresponds to something. I will advertise what it is in a moment. It will be, again, configuration of n distinct points, but instead of being in P1, they are going to be in 3 of P1s. I'll talk about this. It's a beautiful picture. And then you have these morphisms that forget a point, which realize M0n plus 1 bar as the universal curve, or M0n bar. This is, if you understand that this is what you want, then that will guide you in the construction of these objects. But let me give you some intuition. So the picture is the following. You have 2 points. They are trying to collide. They are trying to come together. And before you compactify, they can't, because points are supposed to be distinct. What Knudsen tells us is that in the limit, as the points approach each other, the curve suddenly sprouts another branch, another P1. And these curves end up as points on this extra component. Here's the picture again. This is what happens in the compactification once the points have come together. No, the picture I have in mind is these points come together and then bong, they jump on the extra component. The new component has now 3 special points, P, Q, and the intersection with the other component, P, Q, and the intersection with the rest. And in a P1, if you fix 3 points, then you fix the curve, the automorphism. So up to isomorphisms, this is it. You cannot do anything with these points. These points don't move anymore. Once they land there, they have to stay there. There's no issue that we require for the compactification or whatever. So I hope that you have a little picture in mind for, let me try to draw a movie. We have M04 with this point P4 that is moving around. Well, it's not allowed to hit P1, P2, or P3 in M04, but in the compactification it will. When it hits P1, according to this picture up here, the original P1 sprouts a new P1, and P1 and P4 end up as points in that P1. This is when P1 tries to, when P4 tries to hit P1. And the other picture are when P4 tries to hit P2 and when P4 approaches P3. So M04, remember I tried to point out that M04 bar should be P1, and this is P1 minus 0, 1, infinity. These are the pictures you should associate with the extra points 0, 1, and infinity. And again, you look at these pictures, and each component in the limit has exactly 3 special points. So the configuration as they are, you get your compact variety. There's no moving allowed. Well, what if you are in M05 and you want to have points come together? It might happen that 3 points come together. And then P1 would duly sprout another component, and those 3 points would end up in that component. And now there is a little problem, because here I have 4 points on P1. So the situation is not rigid. These points could move and could try to collide with one another. Now, if they approach each other on that component, well, the tree will just sprout another branch. You see, you get trees by doing this. Every time that points try to come together, you have to produce a new branch of your tree. Now, for M05, at this point, you are in a situation in which each component has 3 special points, and that is the magic that fixes the automorphism. So this is it. You cannot deform it any further. So you can imagine this is now a combinatorial task. Given a number, you have to try to look at all possible trees you can create this way. So that's what points of M0 and bar stand for, according to Knudsen. They are trees of P1s with n-marked points, such that each component has at least 3 special points. This is what stable n-pointed genus 0 curve means for my title. So this is a picture for a combinatorial picture for a point of M09 bar. I was starting with this P1, and then somehow in the process, lots of other P1s were brought into existence, and the points landed on these. And if you look at it, I suppose each component has at least 3 points. So this is a stable n-pointed, 9-pointed genus 0 curve. You can view it as a point of M0 9 bar, or rather as a combinatorial representation of such a point. In fact, yeah, there's a different way to arrange the combinatorics, which is insightful. So let me recast the same information. I have a picture of the same graph in the next slide. I want to consider the dual tree. So there will be one vertex of the new tree I'm going to draw for each component. This picture has 1, 2, 3, 4, 5 components. So I will have 5 vertices. They will be joined by edges if the components in this picture meet. And the end mark points will be represented as leaves. So this is what it is. I have 5 vertices, and 2 vertices are connected by an edge when the components meet. So for example, I suppose, well, let me not try to get it. It should be clear from the picture. And the points themselves become leaves in the new tree. So this is exactly the same information as this. It's called the dual tree. But as you will see in a second, it kind of simplifies thinking about these objects. Stable tree is the tree as above, for which all internal vertices have variance greater than or equal to 3. These are precisely the trees that arise from these other guys. And then the fact that Knudsen proved is that M0 n bar has a stratification, and the strata correspond to stable trees with n number of leaves. The tree corresponding to the big component, and the big open dense set of M0n is just 1 P1 with n points in the dual tree. That becomes 1 vertex with n leaves, numbered. That's the largest stratum, dimension n-3. For M04 bar, the pictures I should draw are these. These are the same pictures I had before, but cast in terms of dual trees. So this is M04 before compactifying. And these are the 3 extra points. I think this was 0, this was 1, and this was infinity in the picture I drew before. And this is it. This is all the trees you can make with 4 leaves, satisfying this stability condition. M05, well, these are the trees you can draw, and then you have to number the vertices in all possible ways, and you can count how many ways you can do that. The advantage of looking at these dual trees is that you can see that they are products of very simple components, and that corresponds to the fact that all the strata are products of the uncompactified M0i's. So for example, if you take this point I've been carrying around, this is a point of M09 bar, I'm going to break it up into trees. Each of them is the simplest kind. It's just 1 vertex and a number of leaves. So if you paid attention, then you know that this is in the picture for M03. There's another M03. There's a third M03, an M04, and M04. And that corresponds to the fact that this stratum is isomorphic to M03 cross M03 cross M03 cross M04 cross M04. It has dimension 2. 2 because this is a point, this is a point, this is a point. These guys are curves. So you see, it's amazingly beautiful. You can now go and draw pictures of trees. Just be careful to obey the stability condition. So each vertex should have a variance at least 3, and then you can do this and figure out what the corresponding stratum of M0 n bar looks like. Now, meaning that it's isomorphism class. It's a tremendous amount of information. So how do you construct M0 n bar? You do it inductively. Because M0 n plus 1 bar is the universal curve of M0 n bar. You can use that fact to construct M0 n plus 1 bar. The map forgets P n plus 1. So let me try to give a little tour for M05. Now, as an example, in 1 level lower, M04 bar is P1, and the map from M05 bar to M04 bar should just forget the last point. So the fibers should look like this. Now, if P4 is not 0, 1, or infinity, then this is what a point of P of M04 looks like. If P4 approaches P1, this is what it looks like. And this should be the fibers of this map, because this is the universal curve. So the fibers of this map should correspond to the points in here. So you need to create a space that has a base that looks like P1, because that's what M04 bar is, and whose fibers are these. Away from 0, 1, infinity, you have this picture, and on 0, 1, infinity, you should have a picture like this. How do you construct that? Well, you first approximate it. Now you take M04 bar, the base, and just cross P1. After all, we are parameterizing points on P1. And that works almost always. Now, if you are here, if you are on a point that is not 0, 1, or infinity, the corresponding fiber looks exactly what it should look like. Now, I had it in the previous slide. Over points that are not 0, 1, infinity, I should see a P1 with 4 points. That's what I see over here, a P1 with 4 points. Then trouble happens when you try to approach one of these points. If P4 comes on 0, then the fiber is not right, because it would be a P1 with 3 points, and these points have come together. So you have to fix that. And the answer is very simple. You're not supposed to let these points come together. You may have an intuition for this. You just blow up. Now, if you blow up this point, then the diagonal will be here. The fiber over P1 will be here. And you sprout a new exceptional divisor that will carry on P2 and P3. I think I said that wrong, but yeah, this is the exceptional divisor. The exceptional divisor meets this, and that is this line. And then I have the diagonal and the section corresponding to P1. You know about blowups. Blowups have this magic thing of separating directions, and these 3 lines have different directions, so they become separated here. And remember, that is the task. The task is to separate the point when they try to collide. Now, look at this picture. It's 2 P1s, the exceptional divisor of P1. This is a P1, and P1 and P4 have landed on those. That's exactly the picture I've been trying to advertise. Do I have it here? There you go. That's the picture you're aiming for. So this is a way to construct a space that does this magic recipe of sprouting extra components and placing points on it. So the bottom line is that M05 bar is the blow up at 3 points of M04 bar cross P1. That's the beginning of your inductive construction. What Kiel does in his beautiful paper is to prove that in general M0 n plus 1 bar is the result of a sequence of blow-ups of the previous one, M0 n bar cross P1, and you just need to blow up along smooth subvarieties of dimension 2. So they are very, friendly blow-ups. All the centers of the blow-ups are isomorphic to products of compactified modular spaces. So it's a very, very neat picture. The general point of the center looks like this. It's just something I plus 1 points on the P1 and j plus 1 points on the P1. The extra point here and here coincide. It's where the 2 P1s meet. So this is what the general point of the center looks like. And this is what you can use to get a recursion formula, the ones I showed at the beginning of the talk. In fact, let's go through that. It's once you have this clear image of how the variety is constructed, then you can draw these conclusions easily. And this is where the Grothendieck group comes in as a convenient way to talk about these things. If you know about the Grothendieck group, you do. If you don't, then bear with me for a minute. The Grothendieck group is just a way to combine varieties together. So take the free abelian group on isomorphism class of variety, but then you allow yourself to identify X with the union of Y and Z if X is the union of Y and Z. So I say it again, the class of X as the sum of Y and class of Z if X is the union of Y and Z. This is joint union. This is called a cis or congruence. Really, if you want to have the class of this and you have this closed subset and Y is the complement, then in the Grothendieck group, the class of X will be the class of Y plus the class of Z. So for example, in the Grothendieck group, maybe I can write for a moment and then promptly erase what I write. In the Grothendieck group, the class of P1 will be the class of P0 plus the class of the complement of P1. And if you remember, I told you that this is called L. P0 for good reason is called 1, so that gives a computation of the class of P1 as 1 plus L. And again, if you have never seen this before, then please go home and play with it. You will prove that the class of Pn is 1 plus L plus dots plus L to the n. So you can do computations in this ring. It's a beautiful ring. People have understood a lot about it. But we don't need this on the slide. Let me erase it. Product makes this into a ring. And there you go. I had the computation a moment ago. Again, if you have never seen this before, do it as an exercise. Pn is this. And notice that you can draw it like this. And again, if you have never seen this before, please think about it. Now, why is Pn going to be this? There's a very good reason for that. Good exercise. By definition, by the way it's defined, literally, this is universal with respect to the all invariants that satisfy the seesaw relation. The Euler characteristic is one of them. The Euler characteristic is additive with respect to disjoint unions, so that means that there must be a homomorphism from here to Z, which sends the class of X to its Euler characteristic. Indeed, people call this a universal Euler characteristic. It's the universal way in which you can satisfy seesaw congruency. Now, the fact that Kiel showed in his paper is that the class in the Grothendieck group of M0 and bar is this. I mean, he doesn't phrase it in terms of Grothendieck classes, but this is a consequence of what he does. So it's just a polynomial in the class of the affine line. The coefficients are the Betti numbers. And by the way, again, if you know this, you know it. If you don't, then beware that the Grothendieck group, a Grothendieck ring, is very interesting. And the affine line is a very special. And the classes like this are called Tate motives in some literature, and they are considered the trivial kind of classes. Convince yourself that the class of an elliptic curve cannot be written as a polynomial in L. Things become very complicated very quickly. So what about M0 and phi bar? I tried to convince you that M0 phi bar is the blowup of P1 cross P1 at 3 points. And then you know how blowups work. You take your reality, you throw away the points, and you replace them by P1s. So there you go. This is a computation, a complete computation of the Grothendieck class of M0 phi bar. And you should compare that with, yeah, this is what it means in terms of Betti numbers. And remember, I had this tree of classes at the beginning. The third line was this. Now you know why it is that. You can compute it yourself. In fact, at this point, you can go home and compute all of these yourself because you have all the information you need, really. Kiel's construction tells me I can do the same in general. There's a reason that if V is non-singular in V or codimension D, then the class of the blowup, this is not mysterious. And how do you get the class of the blowup? You take V, you throw away what you're blowing up, which is a copy of B, and you replace it with a P1, a P D bundle of B, and think about it a moment, this is what you get. And by Kiel, then I have this, that M0 and bar is M0 minus 1 cross bar cross P1, and that's its class, plus stuff that comes from products of lower stages in the construction. Once you do the bookkeeping, it's really not hard to show that this is what happens. There's some combinatorics that you have to deal with, but it's once you know the big picture, now M0 and bar is obtained from the lower level by this kind of construction, then you cannot fail from doing this right. So this is the recursion that I put on the slides at the beginning when I told you Kiel's implies a recursion for the Betti numbers. Well, this is it for the Poincare polynomial. So if you take M0 phi bar and do this computation this way, this is what you're going to do. And again, this is too fast for to absorb in a talk, but you can see that the information is all there, and once you work it out, you get the right term. Now, with this, how do we prove the main result? The main result was an explicit expression for the Grothendieck class. Now, this is already explicit, but it's recursive. This is just a recursion, while you want to solve this recursion and write an explicit class for M0 and bar. Well, Manning gave us a differential equation, and the task is to solve this differential equation. Our result is this. Again, you cannot possibly parse this in a talk, but the result is that this generating function has this explicit expression. So all you have to do, once you come up with this expression, is to prove that it satisfies the differential equation in the initial condition. So you see where the difficulty is not now to prove this. That has to be straightforward. The difficulty is to come up with it. That took weeks. Once we had the formula, then it was more straightforward to prove that it does what it does. All you have to do is to prove that this complicated expression satisfies this differential equation and this initial condition. Now, I don't want to, this is deceptively complicated, I guess. It looks easy, but it's more complicated than it should. Even this, the claim is that if you put L equals 0, then this thing becomes 1. Shouldn't that be trivial? And the answer is maybe, but it is not. It took us a while to be able to prove that this guy satisfies this innocent initial condition. Let me tell you what goes into that. As I say, even verifying the expression equals 1 for z equals 0 is not trivial. And once you plug it in, then you're reduced to this combinatorial expression. And good luck with that. I mean, you run into a combinatorial expression, you can ask Maple whether it is true, and it tells you, sure, for the first 1,000 cases, it is true. That's not a proof, right? How do you prove this? What do you do? Actually, this was last year, and last year, if you try to feed this into an LLM, it would not go anywhere. Things may have changed, but no, I had to do what used to be the case, that is go to the library and look at many books until you find something. Then it was good that I was at Caltech, because Caltech has an actual library. You can go and you have in front of a shelf with actual books in combinatorics, a whole shelf of combinatorics book, and you start looking at them. I did until I found the identity. And in fact, it turns out to be a rather well-known identity, and I could trace it back to 1793 now. So I don't think that people were worrying about Grothendieck classes back in 1793, but somehow this was in some form up there. So you see, the question is, how will you come up with the complicated formula to begin with? And this is where I have this after-the-fact cheating reconstruction. This is not the way it went, but it could have gone like this if I had thought things in a certain way. You have a differential equation. The other thing that Manning gave us is a functional equation, and let me reproduce it here. Manning told us that this generating function satisfies this particular functional equation. The task is to solve for m. This is the way it would work. You postulate that m is n times a new thing, w, and then your functional equation is this. This might suggest to let n have to do with this guy. So this is what I should have done. I should have let n be this expression. If you do that, then your functional equation simplifies after you divide by a power n. You get just another equation in w. This doesn't look much simpler than the original one, but it happens to be simpler. Now, this is what you know. You want a w such that the nth power of w minus 1 times the inverse of w is this particular expression. Then you have to come up with this. This is a combinatorial lemma. And again, you can go to Maple and check that this works for all the m's you want. But no, where does it come from? No, how do you deal with something like this? Well, you look the literature and you find that in fact it is a problem in Polia's Zego, this famous book of problems from 1925, 100 years ago. And there you find a hint that it can be proved by using Lagrange inversion, which is a famous tool in this kind of consideration. So what I'm trying to hint is that 100 years ago, people would have found this easier because it was just a standard exercise in a standard book of exercises. Nowadays, we have kind of lost that connection with combinatorics, I suppose. Now, if you take this beautiful lemma, this lemma has the purpose of expressing the power of x in terms coming from an expression, right? Well, if you apply with this particular position, then this is what you get. I don't want to go through this carefully because it's not material for a talk, but I just want to show that it's not that bad. I mean, you get y because of what you know about w, y is this. And then you can reconstruct what m is. It becomes, because of the lemma, some kind of simple replacement computation. Well, this looks awfully complicated, but it is equivalent to the formula in our claim. So once you get here, you're done. As I told you, the proof can be compressed in a couple of slides. It's not bad once you come up with the formula. And to come up with the formula, well, that's also not bad if you are very strong in combinatorics and you can see all these things. This is maybe already more than you want to know, but I still have some time. I was given up to what time is it over there? It's 5 at this point, right? So I'll talk a little more, but the gist of the main message is already there. Now there is an explicit formula for the Grothendieck class of M0 and bar that is for the Bethe numbers of M0 and bar, and the way you get it is by solving a differential or a functional equation. How you do that? Well, that's no. Every single equation is a little different. Let me tell you more though, because there are things that you can do that let you get into the cohomology of M0 and bar much deeper, and it's somewhat amusing. So I wanted to have a generating function for the individual Bethe numbers, and there you go. This is from the first paper with Stephanie Chen and Matilde Marcoli. This particular generating function for the Bethe numbers can be written in this form. So there exist polynomials with rational coefficients such that the generating function is an exponential times a combination of exponentials. There it is again. Further, these polynomials are understandable to some extent. They are small size, the degree is controlled. They have positive coefficients that took us until the second paper to figure it out. This is a consequence of these formulas I told you about. We could guess it was positive because Maple can give me 150 of these polynomials and you look at them. But we could only prove it after we had these explicit formulas. And really, nothing here is obvious. You have to work your way through rather, I don't know, nasty inductions and so on. That's what our student Stephanie did. Stephanie is now a fantastic graduate student at Harvard, by the way. So the polynomials look like this. So for example, 0 is just a certain number. The first one is this friendly polynomial. So for example, the first generating function would be this according to our formula. And you can work it out and ask Maple to expand it. And you get all these beautiful numbers, 1, 5, 16, 42, 99, 219, 466. And you have photographic memory, so you remember that that is the first coefficients in this big tree I keep putting on the slide. So we have a nice generating function for these numbers, and we have generating function for all of them. The conjecture here is that these polynomials are log concave, and then I will spend a little time telling you about that. Once a polynomial has positive coefficient, you start wondering whether it has more. There's more you can say. Here's a log concavity, a very quick reminder. It's a fashionable concept these days, so it doesn't hurt to be reminded of it. A polynomial with positive coefficients is log concave if these equalities happen. So ai square is greater than the product of the adjacent coefficients. There's a natural stronger condition called ultra log concavity, which will come up in a second, but for now, let's stick with this. This is surprisingly maybe a very significant condition in combinatorics. There's a beautiful survey article, maybe 100 pages or so by Stanley from 1989 that enumerates lots and lots of situations in which polynomials arise which turn out to be log concave. There's a very beautiful example. Jun Ha, Fields medalist from a couple of years ago, his first paper, written as a first-year graduate student, astonishing paper if you ask me, proves that the chromatic polynomial up to size is log concave. And this was an open conjecture for many years. Do you know about the chromatic polynomial graph? That would be a different talk, but if you know about it, then this is somewhat amazing. And so it's a polynomial that counts the number of coloring of a graph. As Jun Ha has taught us, the log concavity is usually a signature of something very deep, what he calls a Kähler package. That's the case for the chromatic polynomial. So there you go. We see that here. These polynomials look log concave. Look log concave means that I can ask Maple to check log concavity, and the first 150 are log concave or something like that. I mean, we have overwhelming numerical evidence. And with the formulas I told you about in this talk, from the paper with Marconi and Nascimento, we can prove that this is actually the case for many. I mean, we stopped at 100 just because. These are infinite families. For all k's, we can show that all of these are log concave. So that brings up the question, is there something like this? Is there a Kähler package behind this construction that takes care of that? By the way, is this enough evidence? That seems overwhelming, but there's a cute story. The coefficients are determined by some other polynomials, and I like playing with maples, so I asked maples to tell me what about these polynomials. Well, they looked positive coefficients, they looked log concave. The first several hundred, I mean, I'm talking about hundreds of polynomials that have very large degree and rather large coefficients, large in terms of how many digits show up. But then the 20th one, which is several hundreds of polynomials down the line, is not log concave, and the next one is even not positive coefficient. It has a negative. So this taught me a lesson. You see tremendous evidence. You want to make a conjecture, you should not make conjectures. I mean, to make a conjecture, you need something stronger. I think here we have something stronger because we have several families that are log concave. It's hard to imagine that that should be a coincidence. All right, so message to the audience, think twice before you make conjectures. Mathematics is very, very deep. I still have a little bit of time, and this is also very beautiful. I did not know anything about the Lambert W function, but that's something else that has extensive literature about. It shows up in all sorts of contexts. It is the solution to the equation Wt exponential to Wt equals t. I write in this solution because there's more than one, but something called the principal branch that is what I'm talking about here. If you make a very minor modification, then you get the tree function, so-called tree function. It's called the tree function because the coefficients in here count the number of rooted trees on n labeled vertices. Well, I told you that Manin obtained his equation by summing over trees, so maybe it's not surprising, or maybe it is surprising, that the generative function we'll be talking about has a reasonably simple expression in terms of this function. So this looks friendlier than the kind of things I put on the board so far, although the polynomial f is not so easy, but there you go. There exists an expression for the generative function in terms of t. T is the tree function coming from the Lambert W. This is pleasant. And the proof, well, again, you have to go back to the library, sit in front of a shelf, and open combinatorial books until you find the one that the combinatorial identity you need. Why is this good? Because you can get asymptotics out of it. So, for example, if you take the Betti numbers and put them into this expression, then you get something that is asymptotic to the tree function as n goes to infinity. Why do I care? Because I have an application. So this is in the paper with Stephanie Chen and Matilda Marcolli. This is again the asymptotics, and this is the implication. The implication is that you have this inequality for very large n. This inequality looks like log concavity. It is ultra log concavity, so it's a stronger condition than log concavity. There we go. So what this says is that the Poincare polynomial of M0 M bar is satisfies this amazing condition of being ultra-low concave if you wait long enough. Wait long enough actually means you fix your eye and then you wait long enough and then the inequality is satisfied. So it's asymptotic in a tricky way. And again, a message from Juni Ha is that we should always care that the polynomial is low concave. This never happens by chance. So no, you would like to dream that actually M0 M bar is a low concave polynomial. And it would follow from this. And again, we came up with this by looking at many examples. Other people came up with the same conjecture. The Poincare polynomial looks like it has only real zeros. And believe it or not, Newton has some remarks somewhere that imply that that means that the polynomial should be log concave. There's a theorem that is usually attributed to Newton that says that if you have a polynomial with real zeros, then it has to be ultra-log concave. So maybe this is the reason why you run into ultra-log concavity, although proving this is so far impossible. Nobody knows why this is true. And people have thought about this. If you look at the Poincare polynomial itself, of course, the Poincare polynomial is a combination of even powers of t, so the statement is that it should have imaginary zeros. But what does it mean? What does a zero of the Poincare polynomial mean? I have no idea, but somehow this nature is telling us that there's some meaning to it, that this wants to be understood. And I'm going to tell you that this fits a separate context. Indeed, Luis Ferroni had come up with the same conjecture. The context is something that has to do with matroids, the popular subject these days. It turns out that this polynomial we're talking about is the Chow ring of the braid matroid. Defining Chow rings of matroids requires a different talk, but it's part of the general idea that you should be able to do in combinatorics things you do in geometry, and you have the Chow ring of algebraic varieties. Well, there's an analog of the Chow ring for matroids. And the fine print is that this is with respect to the minimal building set. There we go. I wanted to mention Kapranov. This is an alternative construction of M0 M bar that implies this. And then the conjecture independently made by Luis Ferroni and Juni Ha is that the Chow polynomial of every matroid with respect to the maximum building set should be real rooted. So this is the context. It's not a particular case of the conjecture. In fact, it's easy to come up with examples in which this other business minimal building set is satisfied and you don't have real zeros. But somehow it fits this general frame of mind. Oops. So the question here is, what is special about M0 M bar or the braid matroid? But why does it make it special? And there are results, partial results on this conjecture based on recursions that are very similar to recursions of M0 M bar. So I have the feeling that there's some truth to be discovered. So I don't think anybody has tried, but it would be possible maybe to prove asymptotic log concavity for matroidal Chow rings the way we prove asymptotic log concavity for the class of M0 M bar. More recent work, and then I will be done. I wanted to point out that since we did this, the literature has grown. There's a beautiful paper by Choi, Ken, and Lee. It's one of 3 beautiful papers. This is characteristic polynomials of M-bar log concavity. Look at the date, it's May of this year. And the abstract has this. Our main focus lies on the cohomology. Actually, what they work including the information of an action of a permutation group. So it's substantially more general than what we do, and they do establish asymptotic log concavity in that context. So they recover this result I've talked about in the last 5 minutes with Marcoli and Chen. Another reference, also rather recent, April, Luis Ferroni already mentioned, building sets, Chow rings, and the Hilbert series, and the established formulas for the Hilbert series of polymatroids, so more general notion. This is the Chow ring we are talking about. These are the names associated with that, and they do it for arbitrary building sets. So they move from the maximal building set, which was the subject of the conjecture I put on the previous slide, to possibly minimal building sets, and among other things, they recover this formula for the Poincare polynomial. So completely different approach. and very nice combinatorial context. And finally, this is really recent because Eduardo Nascimento, who is the third co-author in these papers, just yesterday put on the archive his paper where he uses the formulas in our common joint work to improve the bounds for all concavity. So not only do you know now that it's asymptotic, but you can say precisely that within this range, the inequalities will be satisfied and the range increases as you increase n. All right, so I think this is a good time to stop. There's much more to explore. I hope some of you will take up some of these challenges. It's beautiful material to be thinking about. So thank you very much for your attention.
Thank you very much. And I don't know, there's some questions on the chat.
The chat. I've not looked at the chat at all, and in fact,
that's fine. Some of them were imported from YouTube, but I think it starts from the praise question. Yeah.
Should I try to look at the chat? No, I always get a little confused when I try to move from a slide to. There it is. I found it. There we go. Oof. Yes, lots of questions. Should I go from? Let's see.
Yeah, sure.
Is it possible to compute the degree of M0 and bar using cohomology just like that of the Grassmannian you mentioned? You mean the degree in some natural embedding, or
maybe if you start from the first one to be easier?
The first one was up here. Oh, sorry. Okay. No,
yes.
I get a little confused with yes, connection issues. Sorry for that. Let's see. Questions. There you go. Does the formula for the class M0 and bar have anything to do with the Chow ring of the marine metroid? Yes, that's it is the same thing. I mean, the Chow ring of the metroid is the Chow ring of M0 and bar, and as I mentioned, Kiel proves that that is the same as the cohomology, and the information can be captured by Grothendieck class. So it is the same thing. And again, I would send you to the latest reference by Ferroni and the others for details, I suppose. Yes, you're right. The second question, I think Chow polynomials of braid metroid is also expressed in terms of first and second Steele numbers. My understanding is that this is one of the results in the paper by Ferroni and the others from this past April. Yes, it is the same formula we get. They have a completely different approach to it. And yeah, absolutely. Deform the identity matrix. Can you deform the Steele number to Q? I think I played... we did a little bit and I didn't get anywhere. This is Ballast's question. You had the classical Stirling numbers and the formal identity matrix. Can you deform the Stirling numbers to Q or L Stirling numbers and get your formula? I think I tried without success, but I've not tried very hard. So, and again, if anybody in the audience wants to try to do that, that would be a very beautiful expression. I think that the one I showed you was the simplest of several things I could find, but that seemed the most I don't know, cogent. Is it possible to compute the degree of M0 and bar? Just Grassmannian and degree, degree with respect to some embedding. There are results on recent results on the bounds for the degree. I don't know that these formulas can have an impact on that. Yeah. Any other question?
Yes. Any more questions in the room? Yes, we have one.
Hello.
Hello.
Could you say something about genus G and specifically if the computations you've done kind of generalized to or could be done also for genus G?
As Ettore said yesterday, I'll be honest and say no. No, I don't know. I really don't know if this can be extended to higher genera. I've not tried. And I'm a little scared because then you have to enter the world of stacks. There's a growing group of stacks, but I'm much less familiar with it. And so, no, I've not even tried. Let's put it this way. And I'm scared to come close to higher genera. Again, if anybody in the audience wants to take it on, I think it's a beautiful question, a beautiful it would be fantastic if similar, explicit formulas existed in higher genera. Of course, there's very sophisticated work, for example, by Melody Chan and Sam Payne on the cohomology of MGM bar, and there you have to deal with out cohomology as well. So I don't know. I'm just confessing my ignorance. I don't have the tools to even start thinking about that in higher genus. But yeah, thanks. It's a natural question.
I think we have no more questions in the room. Jared, is there anything else in the YouTube?
Just check. No, I think we need to all unmute those who are able to, and thank the speaker for gracing this occasion and actually speaking. I know it didn't work well because we got late a little bit. We are just
yeah, my fault. Yes. Yeah.
But it's okay. It's okay. We still appreciate, and I think this goes a long way in growing the mathematics in Africa. Thank you for the special talk and the special occasion.
An honor, of course. Yes. Thank you.
Buonasera. Thank you.
Yeah. Thanks very much from the room.